A new phase of modern warfare is now impossible to ignore. The war in Ukraine has shown in brutally clear terms how swarming drones combined with precision missiles can overwhelm traditional air defense and force even advanced militaries to rethink how they fight. Here is the central problem. Using interceptor missiles that can cost millions of dollars to destroy drones worth only a few thousand or a few tens of thousands is economically unsustainable over time. That imbalance has triggered an intense race among major powers to field a new class of weapons that are cheaper per shot, faster to engage, and better suited for saturation attacks. And this is where directed energy weapons, especially high-energy lasers, move from theory toward reality. As of early 2026, the leading programs are no longer confined to laboratories and prototypes. Demonstrations in several countries, laser systems are shifting into operational deployment, practical military integration, and in some cases, the first stages of broader production. Let that sink in. For years, laser weapons were often described as futuristic systems that always seemed just a few years away. Now they're being treated as real tools for countering drones, rockets, and short-range missile threats, especially in environments where the volume of incoming targets can rapidly exhaust conventional defenses. The two countries at the center of this competition are the United States and China. At this moment, the United States appears to lead in technological maturity and combat system integration, while China stands out for rapid deployment, higher advertised power levels, and a strong manufacturing and supply chain base, including rare earth processing. So the question is no longer whether laser weapons matter. The question is who is gaining the advantage and whether these systems actually work under realistic combat conditions rather than in carefully controlled demonstrations. Recent naval testing by the United States provides one of the clearest indicators of where this technology stands. Reports on recent sea-based trials say that a United States Navy destroyer equipped with an advanced laser system successfully shot down 4 incoming drones during a live demonstration, highlighting the growing confidence behind operational laser deployment at sea. According to those reports, the destroyer Preble completed a significant demonstration involving the Helios laser system. Developed by Lockheed Martin, Helios is rated at about 60 kilowatts in its deployed form and is designed not only to inflict thermal damage on drone airframes, but also to function as an optical dazzler capable of blinding or degrading enemy sensors. That dual role matters. A modern laser defense system does not always need to burn through a target to be effective. In some cases, disabling optical seekers, blurring cameras, or disrupting the target's ability to navigate can be enough to neutralize the threat. The test scenario in 2025 reportedly involved multiple targets. That is important because the real challenge in modern drone warfare is not a single incoming aircraft. It is the ability to track, engage, and defeat several threats in sequence before the defender's reaction window collapses. Helios was built to work directly with the Aegis combat system. That means it can operate alongside the ship's radar, sensors, and conventional weapons instead of functioning as an isolated add-on. In practical terms, that level of integration is one of the clearest signs that the United States is treating laser weapons as part of a layered combat architecture rather than a science experiment. The system has been installed on Pebbles since 2022 after earlier phases of testing. The recent results have strengthened expectations that similar systems could eventually be fitted onto more warships across the fleet. The strategic appeal is obvious. A laser, assuming the ship has sufficient power generation and cooling capacity, offers what military planners often call a nearly unlimited magazine. Unlike missile launchers, which carry a finite number of interceptors, a laser can continue firing as long as the platform can keep producing electricity and managing heat. That changes the economics of defense. It allows warships to preserve their expensive missiles for higher-end threats, such as anti-ship missiles, while using lower-cost energy shots against drones and other slower or softer targets. Executives from Lockheed Martin have argued that the successful engagement of 4 drones demonstrates the real potential of laser weapons against mass attacks. Their position is straightforward. Every drone destroyed by a laser is one less costly interceptor missile consumed and one less opportunity for an attacker to drain the defender's arsenal through sheer volume. In the fall of 2025, another major demonstration reinforced that message. During a United States Navy counter-drone exercise in the Arabian Sea, the kills were achieved by heating and damaging the target structures until they failed completely. In a controlled test, that may sound simple. In real operations, especially in regions like the Red Sea, the significance is much larger because naval forces there have repeatedly faced the problem of using extremely expensive interceptors against very cheap one-way drones. This is the heart of the laser argument. If a drone costs only a tiny fraction of the missile used to destroy it, the defender may still win tactically while losing economically. Over time, that can become a strategic liability. The United States Navy appears to understand that clearly. Despite continuing limitations, especially in bad weather such as rain, haze, or fog, current Helios variants are commonly described in ranges around 60 kilowatts and 150 kilowatts. Looking ahead, the United States military is pursuing plans to raise laser power into the megawatt class for future platforms, including next-generation surface combatants. That is not a minor upgrade. It signals a shift from using lasers mainly against drones and sensors toward the possibility of engaging harder and faster threats. The higher the power, the broader the target set may become, provided the platform can support the necessary energy and cooling demands. American planners are not thinking only about one battlefield. These systems are being developed with several theaters in mind, including drone and missile attacks in the Red Sea from groups such as the Houthis and potential future high-intensity conflict in the Taiwan Strait, where swarming systems and saturation attacks would likely play a major role. Now here is where the competition becomes even more intense. China is also investing heavily in laser weapons, and it brings several advantages to that race, including industrial scale, access to rare earth supply chains, and a willingness to move quickly from testing to fielding. By early 2026, China appears to have advanced from experimentation to practical deployment, export activity, and military integration, particularly within naval and ground force formations. In other words, Beijing is no longer merely showcasing concepts. It is trying to turn them into deployable systems. China's most powerful publicly discussed laser weapon is often identified as the Shinan, or a comparable naval high-energy system, though reporting and naming conventions differ across sources. A major version was presented during the military parade in September of 2025, and its principal intended role appears to be shipboard deployment. Its advertised power range has been described at roughly 180 to 250 kilowatts, which on paper exceeds the power ratings commonly associated with current American Helios versions. Reports indicate that this class of Chinese laser has been tested on Type 071 amphibious transport docks and more recently on cargo or roll-on, roll-off vessels used in trials. China also fields a smaller and more widely discussed ground-based system known as Silent Hunter. This weapon is typically described in the range of 30 to 100 kilowatts and can be mounted on trucks or fixed sights for counter-drone defense. Like Helios, Silent Hunter is said to have two principal modes of effect. It can physically damage a target by heating and burning components, or it can interfere with electro-optical systems through dazzling and sensor disruption. Chinese reports have made extremely strong claims about its performance. In some accounts, Silent Hunter is said to have hit every target during realistic test cycles, suggesting a perfect success rate against low, slow, and small threats. That is an extraordinary claim, and extraordinary claims always deserve scrutiny. A perfect test score sounds impressive, but the real question is what kind of conditions those tests involved, how the targets behaved, and whether the results can be replicated in dust, heat, clutter, electronic interference, and the chaos of real operations. At exhibitions such as Airshow China in Zhuhai and the World Defense Show in Saudi Arabia, Silent Hunter drew attention with claims that it could penetrate thin steel at about 1 kilometer and shoot down drones at ranges from roughly 1 to 4 kilometers. Demonstrations like those helped build the system's reputation as a practical and exportable counter-drone weapon. That export story matters because China has not limited this technology to domestic presentation. Silent Hunter and related systems have been marketed abroad, and Saudi Arabia became one of the most closely watched cases. According to multiple defense reports, Saudi Arabia acquired a defense package that included the Sky Saker or Sky Shield concept, built around Chinese radar, electronic warfare tools, sensors, and the Silent Hunter laser. Precise figures for the laser element alone are not publicly detailed, but outside estimates for the broader package have reached into the range of about $10 billion once support systems, radar stations, jammers, training, and technical assistance are included. Riyadh saw clear logic in the purchase. Saudi Arabia faces repeated drone threats against oil infrastructure and strategic facilities from the Houthis in Yemen, who are backed by Iran, while Iran itself remains a major regional rival with its own growing unmanned capabilities. In that security environment, low-cost drones can threaten assets that are vastly more valuable than the aircraft attacking them. A successful strike on oil infrastructure can generate economic damage far beyond the cost of the weapon used to carry it out. Saudi Arabia already learned that lesson in painful fashion. In September of 2019, a coordinated drone and cruise missile attack struck two key facilities, including ABKIQ, the world's largest oil processing plant, and Kurais, one of the kingdom's major oil fields. The consequences were immediate and global. Saudi Arabia was forced to temporarily halt about 5.7 million barrels of oil production per day, roughly half of its national output and about 5% of global supply at the time. Oil prices surged sharply after the attack, with Brent crude rising nearly 20% in a single trading session, the largest one-day increase since the Gulf crisis at the start of the 1990s. The incident exposed a major vulnerability. Even a state equipped with advanced defenses, including American Patriot systems, could struggle against low-flying targets with small radar signatures. That shock created the market for alternatives. Chinese laser systems, advertised as highly effective and comparatively economical, appeared to offer exactly what Saudi planners needed: a way to defend critical infrastructure from repeated drone attacks without relying exclusively on expensive missile interceptors. Chinese manufacturers promoted those systems with confidence. State-linked defense firms described them as capable of very high interception rates, and in at least one widely cited test scenario, a Chinese developer claimed a 100% success rate against a swarm of 21 drones. The marketing was powerful. Some reports even said the system had been sold to around 20 countries, not just Saudi Arabia. For any state under persistent drone threat, that kind of promise was difficult to ignore. But then came the harder question: what happens when the demonstration ends and the desert begins? According to reporting that cited a former Saudi military officer speaking to a defense publication, the practical performance of the system in real conditions fell well below the confidence of the promotional claims. The problem was not that the technology failed to function at all. The problem was that real-world conditions imposed severe constraints. That source claimed that in some cases it could take as long as 15 to 30 minutes of continuous laser exposure to destroy a single drone. If true, that would be a devastating limitation in an actual mass attack, where dozens of drones may be approaching simultaneously and where some targets can move at speeds above 160 kilometers per hour. Let that sink in. If it takes even a fraction of that time to defeat one target, the entire defensive concept begins to break down under swarm conditions. The protected facility could be hit long before the system clears enough targets to matter. The desert environment may have played a central role. Extreme heat increases the burden on cooling systems, and laser weapons are fundamentally dependent on managing heat. If the cooling load grows too high, effective beam performance can degrade. Dust and sand create another problem. Airborne particles interfere with tracking, reduce beam quality, scatter energy, and can weaken the effect on the target. A laser that performs impressively in a clean test range may produce very different results in a hot desert with suspended dust and constant atmospheric distortion. This is where the broader contrast between American and Chinese weapons development is often emphasized. Western systems, especially those from the United States, are generally subjected to lengthy testing cycles that move from ideal conditions to increasingly difficult operational simulations before full-scale procurement and export decisions are made. Even then, testing does not stop. The American approach often involves additional evaluation in realistic operational environments before a system is considered mature enough for wider fielding. Helios is a useful example. Even after successful demonstrations, the United States has continued using it as part of a learning process, gathering data in realistic settings before moving toward broader integration. That does not mean the system is flawless. It means the military appears willing to treat field deployment as a stage of validation rather than the conclusion of it. China's model is often described differently. Critics argue that some Chinese systems are tested extensively in favorable or controlled conditions, then pushed more quickly into serial production, military service, and exports. That faster cycle can create the impression of rapid technological advance, but it also raises questions about whether reliability has been proven under stress. There are several possible reasons for that pattern. One is confidence, or perhaps overconfidence, within parts of China's defense establishment that domestic military technology has reached parity with or superiority over Western systems in selected fields, including lasers and hypersonic weapons. Another factor may be institutional pressure. State-owned defense firms receive research funding and must report results upward through political and bureaucratic systems. In that environment, there may be strong incentives to produce favorable outcomes and present clean success rates instead of exposing weaknesses through harsher testing. A third issue is combat experience. The United States, whatever one thinks of its wars, has spent decades operating in real conflicts after the Cold War. From Panama and Iraq to the Balkans, Afghanistan, Libya, and Syria, that record has given the American military repeated opportunities to identify flaws, adapt doctrine, and refine weapons under operational pressure. China does not have the same recent history of large-scale combat testing. That absence does not mean its systems are ineffective, but it does mean there are fewer real-world benchmarks to confirm how they perform when conditions turn chaotic and consequences become immediate. A fourth factor is export strategy. Beijing has a clear interest in expanding arms sales as a tool of influence. Chinese systems are often marketed at competitive prices, then bundled with training, maintenance, spare parts, and long-term support arrangements that can deepen the buyer's dependence over time. That model is not unique to China, but Beijing has used it aggressively. And once a country becomes reliant on a foreign weapons ecosystem, the relationship can gradually move beyond procurement into diplomacy, leverage, and strategic alignment. The Saudi experience with Chinese laser defense, whether fully representative or not, has therefore become an important case study. It has encouraged other countries to look more carefully at the difference between exhibition claims and proven battlefield reliability. And here is the broader conclusion many analysts draw. America may not always be the fastest producer, and it certainly faces manufacturing bottlenecks and supply vulnerabilities, especially in rare earths. But when it comes to tested reliability and integrated combat systems, the United States still holds a powerful advantage. That advantage, however, is not guaranteed forever. One of Washington's biggest weaknesses has been industrial capacity. Another has been dependence on supply chains, particularly rare earth inputs that are heavily influenced by China. The United States has been trying to fix both problems over the past several years, especially from 2023 through 2025. The country has seen an unusually strong wave of manufacturing investment driven by industrial policy, strategic competition, and the push to rebuild domestic production. Policies such as the CHIPS Act, the Inflation Reduction Act, and newer trade barriers helped drive large increases in manufacturing construction. By mid-2024, spending on factory construction in the United States had reportedly reached about $234 billion and remained elevated through 2025. Foreign direct investment and domestic industrial investment also played a role in reshaping the American production base. The underlying objective was clear: reduce dependence on vulnerable overseas supply chains and rebuild the industrial foundation needed for semiconductors, energy systems, defense manufacturing, and advanced materials. Rare earths are central to that effort. These minerals are critical for electronics, electric vehicles, missile systems, radar components, aircraft, and many other technologies. China's dominance in parts of the rare earth chain has long been viewed in Washington as a strategic problem. Under President Donald Trump, the United States reportedly expanded efforts to break that dependence through a multi-layered campaign. Those measures went beyond executive orders and included direct investment, strategic reserves, allied coordination, and tariff pressure. One major initiative involved building a strategic mineral stockpile, modeled loosely on the logic of the Strategic Petroleum Reserve. In early May of 2026, the administration reportedly launched a national strategic minerals reserve valued at around $12 billion to protect American manufacturers from supply disruptions or pricing pressure linked to Chinese control. Another step involved direct government support for domestic producers. Rather than relying only on indirect incentives, the federal government moved toward taking financial positions and extending large-scale support to rare earth companies operating in the United States, including projects in California and processing expansion in Texas. The idea was simple but far-reaching. If advanced fighters, submarines, missiles, and electronics depend on magnets and materials refined through vulnerable foreign chains, then industrial independence becomes a military necessity, not just an economic preference. Washington also intensified coordination with allies. The administration pushed for a broader mineral trade bloc with members of the Group of Seven and strategic partners such as Australia, Japan, South Korea, and the European Union. The proposed mechanism included concepts such as minimum pricing for critical minerals to prevent Chinese dumping from crushing emerging competitors. It also included the use of tariffs to protect higher-cost domestic or allied production against subsidized imports. Regulatory reform was another part of the strategy. Through new legislation and administrative changes, Washington sought to accelerate permits for mining and processing projects, which have traditionally faced long delays tied to environmental review and local opposition. Supporters of that approach argued that the United States could not afford to wait years for strategic mining approvals while competitors were moving faster. Critics worried about environmental costs, but the strategic direction was unmistakable: shorten approval timelines and expand domestic capacity. The United States also pursued supply diversification through bilateral agreements. Deals and memoranda with resource-rich countries were meant to build alternative supply chains for raw and processed materials outside Chinese control, including cooperation with Australia and selected Southeast Asian states. A further step came when the American Vice President announced a new plan to create an essential minerals trading group with allied participation and floor price mechanisms to stabilize access to critical resources. The reported coalition involved more than 50 countries with strengths in mining, refining, manufacturing, or downstream industrial use. Taken together, these moves point to something larger than resource policy. They are part of a strategic effort to ensure that the United States remains the leading military technology power by securing the industrial and material base required to sustain that position. And this brings the story back to laser weapons. Directed energy systems do not exist in isolation. Their future depends on power generation, thermal management, advanced optics, semiconductors, specialty metals, precision manufacturing, and resilient supply chains. In that sense, the laser race between the United States and China is not merely about who can produce the brighter beam. It is about whose entire industrial system can design, test, field, sustain, and improve these weapons at scale under the pressures of real military competition. Right now, the United States appears ahead in mature integration and operational validation. China appears ahead in speed, advertised power growth, and the ability to move rapidly from prototype to deployment. Export. Those are two very different forms of strength. The unresolved question is which one matters more when war becomes prolonged, conditions become harsh, and marketing claims are replaced by battlefield evidence. A weapon that looks revolutionary on paper can fail in dust, heat, rain, salt, electronic interference, or mass attack. A weapon that seems less dramatic may prove more valuable if it works consistently when the pressure is highest. That is why recent demonstrations by both countries matter so much. They are not just technical showcases, they are signals about doctrine, procurement, industrial capacity, and the shape of future air and missile defense. The age of cheap drones forcing expensive responses is already here. Laser weapons are being developed as the answer to that imbalance, and both Washington and Beijing understand what is at stake. This story is far from over. As lasers move from trial programs into wider deployment, the real contest will be decided not by parade displays or promotional claims, but by reliability, adaptability, and performance in the world as it actually is. And in modern war, that difference can decide everything